It's one thing to look at these massive physical machines and understand how water spins a wheel. It's another to translate that motion into messy formulas, abstract velocity triangles, and exam problems riddled with minus sign errors. In this video, we are going to dismantle these numericals step by step. We'll build from basic velocity calculations all the way up to complex multi-runner university exam problems, ensuring you have a reliable method to solve any geometry a problem throws at you. Look at this diagram. These inlet and outlet velocity triangles provide the geometric foundation for every Pelton equation. On the bottom, at the inlet, we have the absolute jet velocity, v1. It strikes the bucket moving at velocity u. The difference between them is the relative velocity, vr1. When the water exits at the top, it leaves with relative velocity, vr2. The most common error in these problems is the sign convention for work done. Focus on the top outlet triangle. Notice the angle beta. When beta is less than 90 degrees, the whirl velocity, vw2, points in the opposite direction of the bucket motion, u2. Because of this opposing direction, the standard formula calculates the net force by adding the components, vw1 plus vw2. Once those velocity vectors are established, the rest of the toolkit follows. You'll need the hydraulic efficiency equation, the condition for maximum efficiency, where the bucket moves at exactly half the speed of the jet, and the resulting maximum efficiency formula. Trying to memorize these equations without understanding the physical geometry often leads to mistakes. Trusting the velocity triangle is the only reliable way to construct your math and avoid sign errors. Let's apply this logic to a standard problem. This text outlines a system with a 510-meter gross head, 1/3 of that lost to friction, a discharge of 2.2 cubic meters per second, and a jet deflection angle of 165 degrees. Stop immediately at that deflection angle. You cannot plug 165 degrees directly into your equations. The deflection happens outside the math of the triangle. We need the bucket outlet angle, phi, which we find by taking 180 degrees minus the 165-degree deflection, giving us a working angle of 15 degrees. Now we execute the sequence. We calculate a net head of 340 meters, giving an initial jet velocity, v1, of 81.67 meters per second. We calculate the bucket velocity, u, and walk through the triangle to find vr1, vw1, vr2, and a vw2 of 6.64. Now look closely at the final power calculation. The source material sometimes displays a minus sign here. But because our beta angle is less than 90 degrees, vw2 points in the opposing direction. We must calculate the force using vw1 plus vw2, yielding a final power of 7,139.8 kilowatts. When you can spot and correct a typographical error in a textbook regarding a sign convention, you have effectively moved from memorizing formulas to understanding the physics of the machine. Let's add a layer of complexity. Suppose you're handed a problem with a mean bucket diameter and a rotational speed in RPM, but no speed ratio Ku. Active recall. How do you calculate the linear bucket velocity, u, using only diameter and RPM? Pause the video and try to map it out. The geometrical link is straightforward. Velocity u equals pi times diameter times rotational speed, divided by 60. Also, if a problem ever mentions a side clearance angle, treat that simply as another term for your outlet angle, phi. Once you use that RPM calculation to determine the bucket velocity, the rest of the problem follows a predictable path. Your steps for finding power and hydraulic efficiency will mirror the sequence we just executed. Now for the most complex scenario. You have a 3-kilometer pipeline feeding 2 separate Pelton runners with 2 jets per runner. You must also account for transmission and runner efficiencies. When faced with this much data, map the physical path first. Water leaves the reservoir, travels the pipe, and splits to 2 runners, each with 2 jets. That is 4 jets total. Next, assign efficiencies to physical locations. Use the pipeline's 91% transmission efficiency for the net head and the 90% runner efficiency for final power output. Here is a common mistake: calculating jet diameter using total discharge. You must divide the 4 cubic meters per second total discharge by the 4 individual jets, giving 1 cubic meter per second per jet before calculating area. These multi-runner problems are just basic velocity triangles running in parallel. Mapping the physical system first is what prevents variable confusion during your calculations. To finish the calculation, you determine the main pipeline diameter using the Darcy-Weisbach friction equation. Calculate carefully and strictly label your final answers with standard SI units to ensure accuracy. Before you finish, review these 3 technical requirements for Pelton Numericals. First, always convert the jet deflection angle into the bucket outlet angle, phi. Second, verify the sign of VW2 by drawing the velocity triangle. And third, for multi-jet geometries, always divide the total discharge by the number of jets before calculating the jet area. Mastery in fluid mechanics relies on successfully translating physical machinery into an accurate mathematical model. Keep drawing those triangles, and I'll see you in the next session.